Hey guys, welcome to the Big Bear Math channel. We're working out of the 2018 Calculus BC packet, and I'm not sure why I have 2018 in there twice, but it's in there just for extra emphasis, I guess. And we're focusing on question number 6. And as you could guess, if you've been working through some other packets, question number 6 is usually most likely going to be your series question. And this is certainly no exception. So it's a non-calculator question. And we're going to jump right into this bear. This is one that I think is a little bit tougher than normal. The national average on this question was a 2.65 for a score out of 9 possible points. So you think, with our goal of getting a 5 on this exam, if you walked away with 6 out of 9 points, you'd be in really, really good shape on this particular question. So we're starting the day off with, we've got this ln of 1 plus x function that has already been built and created for us. We've got the first 4 terms in the general term. And they've introduced us to f here. And that we want to come up with the first 4 non-zero terms of f as well as the general term. So let's see how we're going to create a game plan to attack that. Okay, so here's my overarching game plan. First of all, we've been given this natural log of 1 plus x. Okay, so that one's building off of that. The first thing you're going to see me do is write this orange function. And you'll notice what I did is I took this x over 3 and rewrote it as 1/3 times x. And to create that, I'm going to substitute the quantity 1/3 x in for each x. So for each of these x's up here, I'm going to replace them or substitute the quantity 1/3 x in place of them. And then the last thing you're going to see me do is take care of this x right here. So when I put these extra brackets around to emphasis is I'm taking a function I've already created and I'm multiplying that entire function by x. So you're going to see me distribute the x to each term. Okay, so that's my overarching game plan. I'm breaking it into really 2 phases. The first phase is going to be a substitution, followed by phase 2 is going to be a distribution of x. So let's see what that looks like. So what you're seeing here in my so-called phase 1, we said we were going to substitute, is every time there used to be an x, and I'm going to put parentheses around each of these. In these green parentheses is where the x used to be, and we just replaced it with a 1/3 x. And then we're going to attempt to clean them up just a smidge. We don't have to get too crazy. So like, for instance, this 1/3 right here, I rewrote it as 3 squared in the denominator. Okay. Now the temptation right there is to turn this entire thing into an 18, 2 times 9, but you really don't have to do that. That's a waste of time. And sometimes that could actually hurt you down the road as far as it could prevent you from seeing a pattern that you need to see. Same thing here, this 1/3 right here, I rewrote it as 3 cubed in the denominator and so forth. And now phase 2, we're going to try to distribute an x into each term. So all we're doing is taking the term that we already, let's see if we can slide here, or take that polynomial we'd already created. I don't know if I can erase that guy right there. Okay, so what we've got cooking here in pink is me taking the previous answer, distributing an x, and when I get to this last term, I've got to multiply an x times an x to the n, which is going to make x to the n plus 1 all over n times 3 to the n. So you notice as I distributed that x, it really had no impact on any of the denominators. Really, in essence, all I did is add a 1 to each of the exponents on top. Now all of a sudden we graduate to part B and they want me to find the interval of convergence, and this is the monster bear. I was shocked. In the rubric, they only awarded 2 points for A. I was kind of surprised about that, but they're awarding 5 points for B. So we're really going to dial in here and spend most of our time today on part B and making sure we get everything we need for interval of convergence. And the number one thing you want to jump on here is the ratio test. And real quick recap of that ratio test says, the ratio test for convergence says that the limit as n approaches infinity of the absolute value of a sub n divided by, or I should say a sub n plus 1 divided by a sub n has to be less than 1. And so we're going to take advantage of that rule to try to find out when this series converges to f of x. So here's how we're going to set this bear up. So to create this n plus first term that we needed, I substituted an n plus 1 for this n, in this n, in this n right here. And that's what you're basically seeing right here out of the gates. So there's my a sub n plus 1. Now, instead of dividing by a sub n, what I'm really doing is now multiplying by the reciprocal of a sub n, which again is me just basically recopying this series or this term up here. Notice what I haven't worried about. I haven't worried about this negative 1 to the n plus 1 because of the absolute values that wrap around this entire problem. So that was something I didn't have to worry about. Now what I'm going to do is I'm just going to work on simplifying this crazy expression. And one of the things that I like to take advantage of is, I guess, what I call decomposition. If I have x to the m plus n power, I can decompose that into x to the m times x to the n. And you're going to see me do that on several of these terms here. So I took this x to the n plus 2 and I decomposed it into x to the n times x squared. Okay. And I did that on a bunch of other terms. And now you can see things start to cancel, like this term cancels with this term. This one cancels with this one. And then really what I'm going to do is I'm going to kind of, in a sense, factor out any non-n terms. What I mean by that is, let's say I take x squared and I divide it by x. The result is x, and I'm going to pull it out here, okay? If I took, let's see, I've got this random 3 just floating around. Let's just pull it out here, okay? The less I have inside here, the better. So as the dust settles, what do we really have? And I should keep absolute values around this 1/3 x. We've got the limit as n approaches infinity. And then inside here, I've got n over n plus 1, okay? Now it's time to evaluate that particular limit. So this limit right here, I use what's called a power fight. And when I compare this exponent to this exponent, I've got same over same. So that just the limit equals 1, and which is awesome. That's best case scenario. So really what we're saying is that the absolute value of x over 3 has to be less than 1 in order for this series to converge to its intended function. And converting that into a compound inequality, we could say negative 1 is less than 1/3 x, which is less than 1. Or in other words, negative 3 is less than x, which is less than positive 3. So that's what I think my my interval of convergence is up to this point. I know anything inside of this interval is going to converge absolutely. Anything outside of that interval is going to diverge. Now, the only thing left to investigate are the endpoints themselves. And so in order to do that, we're just going to start off with x equals negative 3, and we're going to substitute it into that original power series. So I'm going to make a note to myself here. We're checking endpoints. We're going to check endpoints. If I forget to check these endpoints and I stopped right now, I'm only earning 3 out of the 5 points. So we're going to say let x equal negative 3. And we could say f of negative 3 is going to be the summation. We've got our negative 1 to the n plus 1. We've got negative 3 to the n plus 1 all over n times 3 to the n. All right, as I start to simplify that, I've got some fun things that are going to cancel and multiply and all that jazz. I'm getting positive 3 over n, or you could think of that as 3 times the harmonic series. And so that this series is basically going to diverge by the, we could say a p series or a harmonic. All right, we've got p equals 1. It's going to diverge. Let's go check that other endpoint. Let's say let x equal positive 3. So what does f of 3 look like? So we've got our summation, negative 1 to the n plus 1. Now I've got 3 to the n plus 1 over n times 3 to the n. Again, simplifying that rascal, we're going to get, it's going to be an alternating series. Okay, I could say, here's one way you could write what you have left. And now this sucker is going to converge by the alternating series test. And so at the end of the day, my interval of convergence, see if I can pick a different color just so that this answer doesn't get lost, is remember we're diverging on the left endpoint, but we're converging on the right endpoint. So we could say -3 is less than x is less than or equal to +3. Or we could, here's another equivalent type of notation. So that does it for part B. You just did the hardest part, and I think we're going to make part C look real easy, hopefully. So part C says, hey, let f of x, or I'm sorry, let p sub 4 of x be the fourth degree Taylor polynomial for f about x equals 0. Use your alternating series error bound to find the upper bound on the difference between, remember, this would be your approximated value. This is your actual value. So the difference between those two values is going to be what's called your error. So in other words, we're looking for the maximum error when using a fourth degree polynomial. And so real quick reminder here, let's see, so who is p sub 4? P sub 4 in this case is going to be the first three terms because that's your fourth degree polynomial. Fourth degree means you're looking for the exponent of 4. And when you use, in this case, when you use the fourth degree polynomial, your error bound, okay, your maximum error, whoops, we're getting a little crazy here. Your maximum error is going to be what I like to call your first omitted term. So in this case, who's your first omitted term? Who's the first term that you neglected? It would be this term right here. And we don't even care about this negative sign because we're kind of looking for the magnitude of that first omitted term. So we're going to take that first omitted term. We're going to substitute a 2 right here, and that's going to be our error bound. How easy is that, huh? So we could say substituting a 2 is going to give me 32 over 4 times 3 to the 4th. Reducing that is going to make 8 over 81. So that is the maximum error we could experience. And so I'm just going to put the finishing touch. I'm going to say p sub 4 of 2 minus the real f of 2 is guaranteed to be no bigger than 8 over 81. So that's a wrap, ladies and gentlemen. Hey, I hope you found something that was hopeful today. I hope you found something that's going to get you a little bit closer to that 5 that you've worked so hard all year for. If you liked it, please hit subscribe below and share this with your friends. And until next time, take it easy.